Welcome back. In the previous video, I showed you how we can synthesize an alkyne from an alkene, right? In this particular video, we're going to look at the various common reactions that an alkyne can undergo. And you would be immediately surprised that many of the reactions that I'm going to show you, you have learned it when we did reactions of an alkene with pretty much the same reagents, okay, except for a couple that are different. But for the most part, everything you have learned how a certain reagent reacts with an alkene also reacts the same way with an alkyne without any significant difference, okay? And the first of them, something you're all familiar with, and most of you actually did very well with this particular reaction on the exam, and that would be, let's keep the compound the same just for consistency. So this is the compound that we synthesized in the previous video. So let's say this reacts with HBr. Now we all know right away that it is a Markovnikov's addition, right? And we did learn the same reaction when we learned our alkenes, right? And what happens in a Markovnikov's addition is the hydrogen goes to the carbon containing more hydrogens, and the Br goes to the compound containing little or no hydrogens, or less compared to the other carbon, okay? So if we keep that in mind, now with an alkene, we stopped after we added the HBr, right? One time, because there was only one double bond. But in an alkyne, we have two double bonds, so we add it twice, okay? So what does that look like? So let's go ahead and draw out the structure. But this time, I'm only going to write directly the structure without the double bond, okay? Or two of the double bonds. So the Br, as I said, gets added to the carbon containing the little or no hydrogens, and then the hydrogen gets added to the carbon containing more or relatively more hydrogens compared to the other carbon. Now, this is the contrasting difference between an alkene and an alkyne. In an alkene, we stopped after the first addition because typically it's hard to add to a single bond because it's already more stable. Whereas a double bond is a little bit unstable in a sense that it allows addition reactions to happen. And because we have that extra double bond still on the between the carbon and the carbon, we could have added one more, and we did. And so if I draw this again one more time, so this is the product that we are looking at. So just to cosmetically make it look good. So CH3. Okay. So essentially, you add a HBr for each bond, which means that you will have, you know, two Brs and two hydrogens when you're finished adding. All right, let's go ahead, and I think we learned this also when we learned our alkenes reactions, the common reactions with an alkene. So this is the first one. The second one is what happens when the same compound above reacts with a diatomic halogen. And I think I've explained the same reaction. So Cl2 and dichloromethane. Okay. And basically with the double bond, we added one Cl to each carbon containing the double bond. Just like the above reaction, because we have that extra double bond, we're going to add one more set to those two carbons, right? So what does that leave us with? So CH3, CH2, C, Cl, Cl, CH, Cl, and Cl. Isn't that simple? So that's all there is to it. That's the second common reaction. This is again in tune with what we have learned. And the third reaction is, again, this is something you are already familiar with. We did have this particular question on the exam as well. and that is reaction of an alkyne with BH3, tetrahydrofuran, hydrogen peroxide, sodium hydroxide, and water. This is all the reagents you need to accomplish this reaction. And the moment you see that the BH3, the key things to focus is the BH3, because a lot of it is really solvents that actually, so the BH3 and the H2O2 are something you want to focus right away. And we did do this exact reaction when we learned our alkene, which is we add a hydrogen and the OH to where the double bond is, right? So which side does the H goes and which side does the OH goes? Well, this is the anti-Markovnikov's addition. So the OH would go to the side with more hydrogens, and the hydrogen would go to the side with less or relatively no hydrogens at all. So what does that leave us with? So just like we did in the previous case, you know, because we have that extra double bond, we are going to add two hydrogens here, sorry. We're going to add 2 hydrogens here, okay? 1 for each double bond. And then similarly, we're going to add 2 OHs, 1 for each double bond, right? And that's it. The key thing here is to know the hydrogen peroxide is the giveaway clue right here for you, so that when you had your, the H goes to the carbon with less or no hydrogens, and the OH goes to the carbon with little or more hydrogens, right? There we go. So that's your third reaction that you want to know for your alkene reactions. All right, so let's continue with our discussion on, now this is a classic, okay? So reduction, okay? Reduction reactions and oxidation reactions are really, really classic when it comes to learning organic chemistry, okay? Reduction reactions typically means you add hydrogens, okay? Add H2 as a major reagent in the process. And just like how I written it, you add hydrogens to wherever you see a double bond, all right? So let's say we're going to look at 2 different types of reagents that can lead to a reduction reaction. The first one is something you're all familiar with, which is hydrogen over palladium over carbon. Okay, we did learn this when we learned our alkenes. And I think most of you did get this question right on the exam. I would say more than 90% of you did get it right. All you've got to do is add hydrogens to the carbons containing the double bond. So you add 1 set of hydrogen for 1 double bond. So that means we will have a total of 4 hydrogens added to the 2 carbons containing the triple bond. So CH2. Keep in mind, your single bond would always be there, and anything you start would always be there. You basically add a hydrogen, a hydrogen, a hydrogen, and another hydrogen. There we go. Now, this is a complete reduction, okay? That is, if you start with a triple bond, you go to a single bond, okay? Complete reduction, or say 100% reduction, okay? That is, you don't have a double bond left. But what if you're specifically, say, you're starting with the same compound and you say, I don't want to go all the way. I only want to go where I want to stop with the double bond. Then you use something called a Lindlar catalyst, which is again a rich source of hydrogen. Okay, you use Lindlar catalyst, What it does is it doesn't allow the reaction to proceed all the way. That is, it doesn't add four hydrogens or two sets of hydrogen. It only has one set of hydrogen. So that means it'll be just where you will stop with just the double bond. So add one hydrogen to each, and this is your product. Okay, so you must know the difference between, just like how you need to know the difference between a Markovnikov's and anti-Markovnikov's addition, you should know the difference between a hydrogen over a palladium catalyst over a Lindlar catalyst, where with the hydrogen and the palladium and carbon, it goes all the way, so it gets 100% reduction, whereas you could call it 50% reduction. But again, that's not a bad thing. If that's what you're looking for, then that's what you do. But if your goal is to just go from an alkyne to an alkane, which is a single bond, then you traditionally use hydrogen over palladium and carbon as your reagent. All right. So let's continue our discussion further. So I'm going to delete this and bring back another screen right here. So the next reaction is reaction with pretty much the opposite of what we just did, which is oxidation reaction. Okay. Now, just like with reduction reactions where you add typically hydrogens to the reaction medium, in an oxidation reaction, you add oxygen or O2. Not necessarily both O2, but or one O or both O's from the oxygen. Okay, that's where the name oxidation comes from. Even the reagent that you use is pretty oxygen rich. Okay, so let's take our same product that we made. So this is key here. Pay attention to, okay, let's say this is the product we've made earlier in the first video, and we're consistently using it across. KMnO4 is an excellent oxidizing agent. So this is potassium permanganate. Okay, potassium permanganate. It's an excellent oxidizing agent, and when it reacts with an alkyne, this is called a terminal alkyne. Okay, this is a terminal alkyne because you would always end up with one of the carbon will always be CH. Okay, now this reacts different with this than with this one. Let's write an isomer of this one. In that case, you would be left with this, right? You're all familiar with how to write isomers. This is just an isomer of this compound. This is 1-butyne, right? And this is 2-butyne. They're just isomers because it contains the same number of carbons and hydrogens, just different arrangement of the double bond, right? Now, a terminal alkyne reacts with an alkyne that's more centralized in the molecule. Okay, this leads to the formation of an acid, something I will circle and let you know. This is the first time we have seen this group, and this group right here in itself is known as the acid functional group. Okay, any molecule that contains any organic compound that contains C double bond OH is referred to as acid functional group. I didn't want to make a separate video just to say, oh, this is acid functional group. Okay, and the other product would be CO2, because remember, we're breaking this apart and converting it into, so this is an excellent reaction. If you're interested, I will make a separate video for the mechanism, but I believe I have done something very similar to when we learned about I think I believed when we learned osmium tetroxide, I did say that, and it's an oxidizing reaction. And this is very similar to it. Okay, so you don't make another acid, you make carbon dioxide if it is terminal. Let's take this and react it with KMnO4. Now this would have a slightly different effect over your other terminal alkyne. So again, you go till where, oh, see, this your double triple bond is right between this, right? So it's double bond O, OH, plus CH3, C, double bond O, OH. You make two identical molecules. Basically, you're breaking this, right? This looks something like this, okay? This is exactly what happens to something like this. Okay? Okay? Basically, the manganese, this whole manganate, which we say MnO4 minus is manganate, reacts with the carbon. So that's where you're getting your double bond O and OH for each of those, okay? So if the triple bond is in between, then you make two identical sets. In this case, it's identical because they're identical on both sides. But say you have two separate, say instead of CH3, you have a CH2, CH3, you will be getting two different acids, but you make two acids compared to this one where you made a CO2, okay? So this is the contrasting difference between when an alkyne is a terminal alkyne over an alkyne that has the triple bond more in the center or more offset to one side or the other, but it's definitely not on the very end, okay? So that's very important to realize. So you will generate carbon dioxide on the first one, whereas in the second case, you generate two acid molecules. If groups on either side of the triple bond are the same, then you make identical acids. If they're different, then you make different acids, but nevertheless, you don't make CO2, okay? All right, this video is getting a little long, so I'm gonna stop here, and then I got one more reaction for alkyne, which I'll come back and show you in the next video, all right? So stay tuned.